Alright, so we skipped lesson 3.8 because of the shortened school year, but we're on 3.9, and what we want to look at here is a linear approximation. So if you think about it, if we have a function and we have a tangent line, and if we were trying to find the value of the function at a certain point right here, let's say that this was 3.1. Now, if this function is cubed or e to the x or like sine x times x cubed, something that would be really difficult to calculate, we might not want to plug in 3.1 into that very complicated red equation there. But if we think about it, a tangent line hits that point at exactly, let's say that that's 3 actually, and we want to approximate it right just a little bit to the right. Well, the equation of the tangent line is linear. So if we just plug in a point 3.1 to a linear equation, that'll be easy to calculate. So the tangent line allows us to approximate values really close to the point of tangency. And that's what we're going to do. So if you think about if that point is, so we're going to calculate the tangent line at this point, and then we will plug in another point right next to that. So if you think about the equation of that tangent line, it would be y minus y equals, then it would be the slope. Well, what's the slope of the tangent line at that point? The slope of the tangent line is the derivative. So we would calculate the derivative, and then we would have x minus c there. Okay? Now, sometimes they'll solve it for y, and a lot of times when they do that, they put this in front for some reason. So it might also look like this. Anyway, so that's what I was just talking about. So find the equation of the tangent line to this graph. So we want to do that first. So that's going to be, now they're using t of x for that down here, so I'm just going to use t of x instead of y. So we have t of x minus, and we're doing this at 1, 1, so the y coordinate is 1, so minus 1 equals, now we need t prime. So I'm going to calculate that over here. So t prime is going to be, bring down 1/2 and then subtract 1 from the exponent. So it's going to be 1 over 2 root x. All right. So we're going to want t prime at 1 and then times x minus 1. And then if we do that little switch, add 1 to the other side, that was 1/2. If we plug in 1, t prime of 1 is 1/2. Okay. And then this would still be x minus 1. Now, if we plug in the actual square root of x, and we typed in these in our table and set that up, this would be 94868 ... And this would be 0.99487 ... And this would be 1, and this would be 1.00498, and this would be 1.048808. Okay. Now, if we do the tangent line right here, if we plug in 1, that would be 1. Now, if we plug in 0.99, that would be 1 over 100. So that would be negative 1 over 100. So this would be negative 1 over 200. So that would be 0.1 minus 1 over 200, which would be 0.995. Okay, it would be 199 over 200. And if we plug in 0.9, that would be negative 0.1, which is negative 1/10, which is negative 1/20th. So that would be 19 over 20, which is 0.95. And if we similarly think about it on the other side over here, we would have those. So you can see that that is really close. So it would be much easier to plug this in, and we can actually calculate it, possibly in our head, whereas the square root of 1.01, most of us can't calculate that in our head or even on paper anymore. There is a way to do it by hand, but most of us don't know anymore because we have calculators and we don't need to. Okay, so moving along, differentials. So if we have y equals function, you can read this yourself, it's differentiable. The differential x is denoted by dx, is non-zero number. The differential of y is equal to f prime times the differential of x. And delta y can be calculated using this, the change in y, and that's can be approximated by this value here. So it's just easier just to look at what that is. So let's see, dy was up here. So dy is equal to f prime times dx. Okay, so f prime, y prime, is going to be 6x. So the differential of y is equal to the derivative, and this is at 2. So if we fill that stuff in, that would be 6 times 2, that's the derivative, and then times delta x, which they're telling us is 0.1. So we're just plugging in right here. So that's going to be 12 times 1 over 10, which is 1.2. Okay. Now, if we look at the change in y, that's going to be this, which is 2.1, 2 plus the delta x, which is 0.1, minus f of 2. Okay, so this is going to be 3 times 2.1 squared minus 5 minus 7, because we would have 3 times 2 squared minus 5. So that would be 7. So this squared is 4.41, and then that'll be minus 12. And this is 13.23 minus 12 is 1.23. So you can see that that's a bit more work than this, and especially if this function was a lot more complicated, then this would get a lot more complicated. So it's a lot nicer to just use the approximation here, the derivative at c times the difference of x. Now, one more thing, I think we've mentioned this before, but if you're having trouble with your calculator, one thing to try is to go to the home screen and in there hit second F1, which is F6, and then go to number 2, which is new problem. Hit new problem, it'll come up on the screen, hit enter, and it'll clear out everything that you had typed in the home screen. And sometimes that'll solve, if you're having some issues, that'll fix it. Okay. All right. So we can use these differentials to find the error in a measurement. Okay. So this has some information in it, but the main idea is this right here. You're going to take the derivative at the value times the error in x, and that'll give you the error in your final answer. So the last couple years, this was on the third and fourth test of the second quarter. I'm not sure this year, but this has been a test question. So what you want to do here is identify a few things. So the first thing is you're talking about the area of a square. I don't know if that's the first thing, but that's one thing, is we're talking about the area of a square. So we can write the function down. So the area of a square is side squared. Now you can see from the formula up here we need the derivative, so we could just calculate that now. So f prime of x is going to be 2x. Alright? Now, they told us that the measurement was 10 inches, so that's going to be x. So that's 10 inches. And then the last thing here, before we start to try to use the formula, is the error. And in this case, that's plus or minus 1 over 32 inches. Okay? So, if we look at delta y is the derivative, which is 2x, times delta x. So, x was 10, and delta x was plus and minus 1 over 32. Now, if you think about it, this 10 is in inches, and this plus or minus 1 over 32 is in inches also. And if you think about it, what we're calculating is the error in the area. What's the error of the area going to be? So this is going to be 20 over 32 plus or minus. So 20 over 32, 4 goes into those 5/8. So it's 5/8 square inches. Okay. So I don't think this is a big deal, but if we have a function, we take the derivative of it, it looks like this. And if we multiply both sides by the dx, that's called the differential. But if you think about it, there's not much difference between these. As far as the practicality of doing the problem, you do it the same. The last thing is you put a dx on the other side. So if we try this out, hopefully you see that that's, so you should be able to pause this probably and do all three of these. But that's the product rule. So that's going to be, so we would start off, I don't even want to do that, but it'd be dy over dx. But I know that I'm going to multiply it by dx, so I'm not even going to write that down. So now the derivative of the first thing would be 1 times the second thing would be cosine plus the derivative of the second thing, or the first thing times the derivative of the second thing. So that would be negative cosine. So then that would be negative x, I say cosine, I meant sine. So negative sine. The derivative of cosine is negative sine. And then, because I didn't want to do another step, I'm going to multiply both sides by dx right there. Alright. Now, same thing here. This is going to be dy dx, but I'm going to remember that I'm multiplying by the dx, so I'm just going to keep that in my head and take care of that. So if we bring, again, I want to try to do multiple steps at the same time. I'm going to bring the negative 17 down, subtract 1 from that, and then use the chain rule and multiply by that 2. So I have negative 17 times 2. That's going to be negative 34. And then that'd be negative 18. So that's going to be 1 plus 2x over 18. Okay? All right. Now we're going to have a quotient rule here. So remember, quotient rule starts with low and ends with low. So that's going to be low d high, which is negative 3x squared, minus high d low, which is negative 1, over low squared. And it would be dy equals that dx, but we're going to simplify that a little bit first. So if we multiply this out, that's going to be, get a different color over here. So that's going to be negative 6x squared plus 3x cubed, minus times a minus, that's going to be plus 1. That's going to be minus x cubed. So that means dy is going to equal, we have 3x cubed, that's going to be 2x cubed, minus 6x squared plus 1 over 2 minus x squared dx. Alright, so I don't remember that coming into play very much. I don't remember that being on an AP test, but there you go. Now this one, definitely, it's on a bunch of tests. It'll be on a bunch of my tests. It'll be on the AP test. And we're going to show you an AP question after this. Function is twice differentiable with this, this, and this. What is the tangent line approximation of 1.9? So it's so simple. Just memorize what to do when you see this. So the first thing is, you see it says tangent line. So we need to write the tangent line. So that's going to be y minus y equals, and then you need the slope, but the derivative is the slope. The derivative at 2. So that's going to be 4, and then you're going to have x minus, and the x coordinate is minus 2. So there's your equation of your tangent line. Now you were asked to approximate 1.9. So if you add 1 to the other side, and then if you plug in 1.9 right here, you're going to get that. So that's going to be minus 0.1 times 4. It's going to be negative 0.1. So times 4 is going to be negative 0.4. So your answer is going to be 0.6. So that's your tangent line approximation. Now it says, is that greater or less than the true value? So if we look at the second derivative here, let's think about what that means. So we have the second derivative is greater than 0. So that means that f of x is concave up at x equals 2. So if it's concave up, and we're doing a tangent line, no matter where we put the tangent line, this side or this side, the tangent line is going to be below the actual value. So the estimate, the estimate is less it's an under approximation. And why? This is our reason, all this. Saying that it's concave up, the tangent line will be below. And we're going to do a bunch of practice AP tests for most of the fourth quarter before the actual test. So you'll see how they word it, and that'll give you some better idea of how to write your answers. So here's an AP test question, a free response question. So take a look at that. And let's see what we might have to do with that. So when you are looking at a free response AP calculus question, you want to take notes on the question. That'll help you. So as you read through the question, you look for things. So the volume of a hot air balloon, spherical volume of a sphere. So that's going to be, try to write that down, pause, 4/3 pi r cubed. Okay. And expands inside this. Expands. Okay. The radius of the balloon in feet is modeled by a twice differentiable function. R T is measured in minutes for 0 to 12. Okay. Graph is concave down. Table. Okay. Those are R primes. It's the derivative. The rates. Those are rates. Here. The radius of the balloon is 30 when t equals 5. Okay. Estimate the radius of the balloon at t equals 5.4. Use the tangent line approximation at t equals 5. Okay. Then estimate is your estimate greater or less than? Okay. So let's start with the tangent line approximation. So right here we have 530. That's a point. on there. Now we also have the derivative at 5, which is 2. So that's going to be our tangent line. So if we have y minus y, so we're going to have y minus 30 equals, then the slope, which is 2, and then x minus 5. Okay? So that's probably worth a point. Then we're going to plug in 5.4. So we're going to add that 30 over, and you're going to put 5.4 in here. And that's going to be 0.4 and 2. Now, on the AP exam, we would stop right there. Okay, because we don't want to make a foolish mistake. But for practice, because on a multiple choice, we need to keep going. So 0.4 times 2, that's 0.8. So that's going to be 30.8 feet. To estimate the radius of the balloon at time 5.46. Now, is your estimate greater or less than the actual value? Well, it said that it was concave down the whole way. So if it was concave down the whole way, that means our tangent line is going to be above, and so when we go to approximate, that's going to be greater. So it's concave down, concave down, R is concave down from 0 to 12, so it's going to be greater than the true value. And that's probably worth a point also. So that could be worth up to 3 points. Definitely a point for that, and maybe a point for the tangent line approximation as well, possibly. Or it might just be worth 2. Okay, now find the rate of change of the volume. So this is a related rates question. So as soon as you see that, the rate of change of the volume, you should be thinking dV dt. And that's going to go back up to the sphere here, and we're going to take the derivative of that, so that's going to be 4, bring the 3 down, they cancel, 4 pi r squared dr dt. Now, when t equals 5, the radius was 30. So that's going to be 4 pi times 30 squared. And then we need dr dt. And at first you might be thinking, well, what? But dr dt at 5 is right here. It's 2. So we can multiply, and that's feet per minute. And this was feet. So it's going to be squared. So it's going to be feet cubed per minute. So 30 squared is 900, and 900 times 8 is 7,200, so that's going to be 7,200 pi feet cubed per minute. Alright, so this is the 2017 test, number 4, and this is, I've only seen it one time, but it's pretty tricky. And the reason it's tricky is that the derivative is in terms of y, basically, which is a little bit strange in this context. So, and what I mean by that is, if you look at this, the point here is 0.91. So, but h is the y, and the derivative basically has a y in it. So this is the only time I remember seeing this. So here it is, write the equation of the tangent line. So the equation of the tangent line, we need the derivative at 0, h prime of 0. So that's, well, the first place it gets tricky is right there. So we need to plug in 91 for h. Okay, so what's that? 364. So that's going to be negative 1/4 times 64, which is negative 16. So now we can write the equation of the tangent line, and we actually don't have to use slope. We don't have to use point slope form like we normally do, because this is the y-intercept, because x equals 0. So we could go straight to h of t equals, that's the slope, so it's negative 16t plus 91. So that's the equation of the tangent line, and now they want us to use 3 for t, so that's going to be negative 16 times 3 plus 91. So that's going to be negative 48 plus 91. So that's going to be 3. Borrow 1 off there, that's going to be 43. So that's going to be 43 degrees Celsius. Now that kind of looked easy, but that's because I kind of had it memorized about what I needed to do there. But that really throws people off, that the derivative had a y in it, basically. Okay? Now, we're going to go ahead and do this other part of this question too, because it's valuable. So it says use the second derivative. Oh, and we need to, it relates to this. So use the second derivative to determine whether that's so. Let's just find the second derivative instead of talking about it. So the derivative of this is going to be negative 1/4 dh dt. And then the derivative of that's a constant, so that's 0. Now the trick here, and we've had this in some notes and things, is we have to substitute that back in. So the derivative of h dh dt is right there. So if we plug that back in, we have this. Okay? And if we do that, that's 1/16. We have h minus 27. And if we do sign chart here with 27, if we put in 20, that's going to be negative, and this is going to be positive. So if we go back up to our question here, it said that h is greater than 27 degrees for all the times. So h of t is greater than 27 degrees. So that means we're over here. So that means the second derivative is greater than 0. So h of t is concave up. So if it's concave up and we have a tangent line, so that's going to be an underestimate. So we have an underestimate. Okay, dang it, I think that was behind. Well, that's not that bad. All right, I'm going to break these notes into 2 parts because I have to open up a Google Meet, and I just worry that sometimes it gets cut off. So part 2 will be some review multiple choice questions.